Welcome back to RAW. RAW is the open source software tool for manipulating X-ray small angle scattering data. In this second demonstration, I'd like to show you all of the important tasks you need to know when visiting a synchrotron. So the first thing you want to do is look at the Python toolbar and find the load settings option. Okay, if I load settings, what I want to do is search for a config file. So in my desktop, I have a standards folder, and this is the data I collected on F2 Beamline, and you'll notice that there's a .cfg file. Your Beamline scientist should provide you with some sort of a config file, and this contains the beam center, the distance from the sample to detector, the wavelength of the X-rays, and so forth, including the mask for integrating profiles. So all of that information should be provided to you when you leave the synchrotron source. You can also generate these yourself, and I'll show you how to do that in a future demonstration. So I'm just going to open this and let it load. So once again, what we want to do is go to the Files tab and look at this open folder icon, and I'm going to navigate my way to my standards folder, which once again is on the desktop right here, and I'm displaying all of the different files that are in that folder. I'm really interested in seeing only TIFF files this time because we're using a Pilatus detector in this particular experiment, and that generates these special TIFF files. So if I scroll down, we're going to look at the lysozyme buffer information, and I double click on a lysozyme buffer. What you see is it's loaded that Pilatus image and automatically performed a radial integration. So you can see your Q and your intensity function here. If you want to see what the actual image is like, you can click on this image tab, and you have to adjust the contrast using that special contrast adjusting tool down there and set this to something very low. So you can see there's not much to see in a buffer profile. Here's the beam stop diode, and the direct beam is underneath of this, and then there's just a tiny bit of scatter here, and it's very, very low level. So there's not much to see. You can actually, if you want to simultaneously look at your image and your profiles as they come out, you can just sort of drag the tabs to different places on the screen using the Python GUI. Okay. So what we'd like to do is load all of these lysozyme buffer profiles. So what we usually do, what's typically done in a SAX experiment, is we do small exposures and then add them together and look for radiation damage. So there's no radiation damage in the buffer, of course, but we want to do exactly the same kind of data collection strategy for the buffer as the protein. So I've selected all of those remaining buffer images, and I'm going to hit the plot button, and that will automatically load them all. So you can see they've all superimposed, and they really all superimpose to within the noise level of this experiment. So if I go to the manipulation window and collapse these profiles, you can see I have 15 profiles here, okay, and they're really all right on top of one another. So I'm just going to select all of them by using my shift and left click. You can see that they're all selected, and then hit average and remove. So remove will eliminate all of the individual profiles from the memory, and it will keep just the average that we just calculated. So you can see A underscore lysozyme buff. Okay. So it's kind of a flat curve. It's water mainly. So let's go back to the file menu and load the actual lysozyme standard. You can see here it's lysozyme ST. I'm going to do the same thing. I'm going to select all 15 and do a plot. And you can see they all appear on the screen. So if we go to manipulate, collapse the boxes to their minimum. Now here it's very important to check to make sure that you don't have any kind of radiation damage. So I'm going to click the hide all icon and then select just the first lysozyme and the last lysozyme. And you can see that they overlay perfectly. We've oscillated our sample. There's no detectable radiation damage. So that means we can just merge them all. You don't have to recheck all of them. You can select all of those curves same way as we did before using left mouse click and shift, and then just hit average and remove. And we have a nice smooth averaged curve. So let's put the buffer back in, and you can see here this is characteristic. Buffer is flat and you have some signal here. Nice signal, and it's sort of a curve upward like this is a good sign. It means you're reaching a Guinier regime. So now what we need to do is to actually subtract the buffer from the protein signal. So we make a star, we mark the buffer with a star, and then we select the curves that we want to subtract the buffer from, and then hit the subtract button. Okay, and you'll notice that an S_A file has appeared with a little red star next to it. And in the second window, you've got a characteristic lysozyme scattering pattern. I'm going to put that in log-lin mode, just because that's a more an easier way to look at things. So the next step that we want to do is we want to select that newly subtracted profile and push our right mouse button and move down to Guinier fit. So the first step in any analysis of scattering data is to do the Guinier analysis. That will bring up a sub-window that you see here. It's a plot of log of intensity as a function of Q squared. And you can see that it's very linear. So Guinier's approximate law says that if you look at the very small angle part, it's essentially a line. So the way we determine the slope of that line and the intercept is we need to tell the program which part of the curve we want to fit. And you can see there's a dashed red line here and a dashed red line here. That means that the program is going to use all of these points in the fit. Well, we don't want that. We want to just use the points up at low Q. So you can click on the Nmax item in the menu here, and it will bring your Q maximum in. Alternatively, you can type some value, and it's kind of a shortcut. So how far do you go in? Well, there's a rule of thumb that goes the Q value times the estimated radius of gyration should be about 1.3 or less. So we see we've actually gone in a little bit too far here. Okay. All right, so that sets our maximum Q. The minimum Q is pretty good. You'll notice sometimes there's a bit of noise here at very low Q. That's because sometimes there is beam movement. You're looking for a small difference in very large signals, so your signal to noise is declining. And sometimes you might want to, cut off some of the noise at the very end of the curve. You can see doing that doesn't make a whole lot of difference at all in the radius of gyration. So I'll leave it at about 0.01 inverse angstroms. And you see that it's estimated the radius of gyration is 14.1 roughly. The published value for lysozyme is 14.3 plus or minus 0.7, so that's good. We also know the concentration here is 4.2 mg per mil. That will allow us to use this lysozyme as a standard for estimating molecular weights. So I'm just going to hit the OK button at this point. Oh, I should point out that the second curve here is actually the difference between your line and the actual data. And you want to see more or less randomly distributed points. You don't want to see any kind of an arc or bow shape here. And this is pretty good. This is pretty good. That means there's no aggregation. And you have a monodispersed sample. So there are just a couple more things that you need to know how to do. You need to know how to save your data. So first of all, you can see I still have selected my subtracted curve. To save that curve, you just hit the Save button, and you navigate to the folder where you want to save it. You hit Choose, and in this case I've already got a file there, but I'll just say yes and overwrite it. So that saves your subtracted profile. What you also want to do is you want to save your Guinier analysis information. You'll notice if I just hold my mouse over the Information tab, it actually gives me a reminder of what the radius of gyration, the concentration, and the I0 are. You'll also see if I highlight, that information appears across the top of the screen here. You can edit that information. It's not saved to disk until you click your right mouse button and you go down to Save Analysis Info. So I'm going to do that. and it will allow me to build a spreadsheet and select which columns I want in my spreadsheet. I like concentration and Q start and Q end, QRG min, QRG max, RG, quality of the fit, I0, and last but not least, any estimate of the molecular weight. That's the typical list. You can have anything you want there. Okay, and then it asks me where do you want to put that? So I'm going to call it standards sheet. Okay, and it will save that as a spreadsheet compatible file. What I usually do is wait until I have a whole sheet full of subtracted profiles with Guinier analysis, and I save them all at once. So that means you can read in just one spreadsheet with all your values instead of having to merge a bunch of single spreadsheets. It's just a little bit less work. There's one last thing I want to tell you about, and that is when you're actually on the beamline, you may want to watch the data as it's actually coming off the instrument. And so you go to online mode, and you'll see there's an online option. And that allows you to select the folder for your program raw to watch. And whenever some new file appears, it will automatically read that image in, integrate it, and produce a profile for you. So that's a very handy thing that you'll need at the synchrotron. This concludes the second in the series of raw software demonstrations.